Okay, so last time, if you remember, we were talking about Amerton's law. There were two parts. The first part says that the rate of change of pressure with respect to temperature is independent of temperature if we're looking at a gas. And this is an important way of measuring temperature, because if we draw a graph then of the pressure of a gas as a function of temperature, we can measure, say, the pressure at 0 somewhere here, the pressure at 100 somewhere here. The first part of Amerton's law says that this should be a straight line, right? So there should be a straight line going between these points. So that means that by measuring the pressure of the gas, we can work out the temperature. And this gives us a way of measuring temperature by measuring the pressure of a gas. Okay, this is a gas. Okay. So today we're going to look at a consequence of the second part of Amerton's law, which says that if you take this gradient and divide it by the pressure, then you get an answer which is the same whatever gas you use. So whether you use nitrogen gas or oxygen gas or helium gas, this quantity at a fixed temperature always turns out to be the same. And a consequence of this, which is very important in thermodynamics, is something known as absolute zero. So that's going to be the first of our topics today. Now you see, because this is a straight line, in theory, if you go down low enough in temperature, it should still be a straight line, you will reach a point at which the pressure of the gas goes to 0. Just by going down and down, this is a straight line, so eventually you will reach a point, in theory, where the pressure of the gas goes to 0. At this temperature. The pressure of the gas goes to 0. Okay, so a question is, how do we calculate this temperature? Right? How do we calculate this theoretical temperature at which the pressure of the gas goes to 0? Well, suppose that we know the pressure and temperature values of the gas at some other point, let's say here. So suppose we know that at this point temperature is T0 and the pressure is P0. So if pressure is P0 at temperature T equals T0, then the pressure will go to 0 when temperature goes to the value of T0 minus P over dP by dt. P0. Okay, hopefully that's not too difficult to see why. This height is P0, right? And the slope of the graph is dP by dt, which is a constant. So if I divide the height by the slope, then I will get this length here. So that's just that term. Okay. But the significance of the second part of Amerton's law is that this P0 divided by dP by dt is the same for all gases. Okay? I can write this as equal to 1 over P0 dP by dt. Right? That's clearly the same thing. And Amerton's law says that this is the same for all gases. Now what that means is if I take another gas on this graph and I plot the pressure and temperature for this gas as well, suppose it goes here and here, this is gas number 2, and I do the same thing, I take the line back until it hits 0, it will hit 0 at exactly the same point. So whichever gas you use, the pressure of the gas theoretically always drops to 0 at the same point of temperature. Okay? And this is true whatever gas you use, so I can use another gas which looks like this. 3. You get the idea. So the gradients are such that they will all go to 0 at the same point in temperature. And this is the point we call absolute 0. So therefore, in theory, because you can't really get there exactly, but in theory, P goes to 0 at the same temperature for all gases. So this is what's important, is it is universal. It doesn't depend upon the system. This temperature at which the pressure goes to 0 is always the same. So this temperature is called absolute 0. Okay, and if you do an experiment and you measure this pressure temperature gradient, then you can calculate what its value should be, and we now know the value pretty accurately. In the Celsius scale, that's the one where 0 is the freezing point of water and 100 is the boiling point of water. In this scale, we find that absolute 0 is equal to minus 273.15 Kelvin. Oh, sorry, minus 273.15 degrees C is absolute 0. Okay, so this was originally discovered by looking at the properties of gases, and you can't really, originally they couldn't really get close to absolute 0. These days we can. But this absolute 0 turns out to be important for any system. So whether it's a gas or it's a liquid or it's some more complicated combination, it's always true that when you reach absolute 0, this temperature, the system will go into its minimum energy state. So this temperature corresponds to the minimum energy state of any system, whether it's a gas or a liquid or, let's say, a composite. That's the first point I want to make. Absolute 0 is the temperature at which any system will go into the minimum energy state. That's the first point I want to make. The second point I want to make is that the way I've drawn it for these gases, it's not really exact. Okay? Although it's approximately a straight line, and for some gases it's very good approximation to say it's a straight line, it's not exactly a straight line. Okay? So this picture is a simplification. So that's the last point I want to make, is that dP by dt is constant, that's Ampère's law. Is only approximately true and it's only approximately true if you are far away from the boiling point. So for gases far away from the boiling point. And it's best for gases which are weakly interacting. So, for example, the gases which give you the best straight lines are things like nitrogen gas, helium gas, and so on. These are gases which are weakly interacting, and they give you the best straight lines. And the reason for that we will see later on in this course. Now, this absolute zero gives you a way of defining temperature as well, and this is what's called the Kelvin temperature scale. Which you probably know about, and it's usually given the symbol K. So the Kelvin temperature scale, you start by saying that this point is zero. Rather than saying zero is the freezing point of water, or giving some system-specific definition of the 0 point, we can define absolute zero, which is the same for all systems, as being the 0 point in our temperature scale. So we define that absolute zero is equal to 0 Kelvin. That defines the 0 point. Then we have to say how big is a unit of Kelvin, like how much is 1 Kelvin change in temperature, and it's defined so that 1 Kelvin is the same as 1 degree Celsius. So the scale is the same as the Celsius scale. So we define the change in temperature of 1 Kelvin is the same as the change in temperature of 1 degree C. So the unit scale is the same, but the 0 point is different. So the fact that the size of the scales are the same makes it easy to convert between Celsius and Kelvin. You just have to add 273.15. So for example, if I look at the freezing point of water, so this is 0 degrees C, this is 273.15 Kelvin. If I look at the boiling point of water, this is 100 degrees C. So to get it in Kelvin, I add 273.15, and I get 373.15. So it's easy to convert between Celsius and Kelvin temperature scales. Okay, so now I want to go and talk about something which is quite different, but which you need to know in order to answer the quiz this week. And this is related to something I talked about at the start of the course. I showed you this apparatus, which is invented by Joule, and I told you its purpose is to show that heat is a form of energy. And the way it worked is you let this mass drop so it loses gravitational energy. That energy goes into the water through these paddles, and by adding energy to the water, you increase the temperature of the water. So what Joule measured is how much energy is necessary to change the temperature of the water. Okay? And this depends upon the liquid. If you use water, you get a certain value. If you use alcohol, you get a different value. If you use, say, olive oil, you'll get a different value. So it depends upon the substance that you're using, but it's known as the heat capacity. So, well, I'm going to call it the heat capacity. It's also known as specific heat sometimes. I'm going to use this terminology. So that's the idea of it, how much energy, how much heat, which is a form of energy, is needed to change temperature of a system. So I'm going to define two different kinds of heat capacity which are very closely related, but they have different units, which sometimes confuses people. First of all, you can talk about the heat capacity of a substance, like, for example, of water, of mass. I suppose we've got a mass of this substance M, so we've got 100 grams of water or whatever. This is given the symbol C for heat capacity, and it's defined as the rate of change of temperature with respect to heat per unit mass. So heat is usually given the symbol Q, and this is a notation I will use throughout this course. So whenever you see Q, it means heat. T is temperature, obviously. So the units of this, if we're using SI units, well, heat is an energy, so that's joules, then mass is kilograms, and temperature is Celsius or Kelvin. So use Kelvin. That's the unit. So that's the first form of heat capacity. We can talk about heat capacity of water, or heat capacity of alcohol, or heat capacity of steel. You can also talk about the heat capacity of a whole system. So if I take something like this eraser, which is made up of many different things, it still has a well-defined heat capacity. How much heat do I need to give it to change its temperature? Okay. So we can also talk about the heat capacity of a system. Of a whole system. And in this case, we don't divide by the mass. Okay, so we define it simply as how much heat is necessary to change the temperature. Straight derivative. Okay, and this one has units of just joules per Kelvin. Now, the way I've defined heat capacity there, there's a little bit of uncertainty in the definition, because when I say how much heat you need, it depends upon how you treat the other properties of the system. For example, if I was looking at a gas, you remember I've talked about two different ways you can contain the gases. First of all, you can just put a gas in a box at fixed volume V. Okay? Or I could put the gas in a kind of movable box where I apply a constant pressure to the gas. And I can calculate the heat capacity, so I could try and heat this system with some fire, like this is fire. Okay? And I can measure the heat capacity in this case, and I can measure the heat capacity in this case. But they're different. Okay? It depends whether are you doing the experiment at constant volume, or are you doing the experiment at constant pressure? And you get different answers for each of them. So we need to distinguish the two. So there's heat capacity at constant volume. So in this case, we take the partial derivative of heat with respect to temperature, holding the volume constant. So you remember I introduced this notation last time. This line with V means that V is constant. Okay? Or we can have the heat capacity at constant pressure. So this is where we do the calculation, but we do dq by dt, constant pressure. Okay? And the answers you get are different. For solids and liquids, the answers are not very different, but for gases, it's a big difference. So for gases, it's very important whether you keep the pressure constant or the volume constant. Okay? So this one is usually given the symbol C with a little v to denote the fact that the volume is constant. And this one is C with a little p to denote the fact that the pressure is constant. Okay? And it's always true that the heat capacity at constant volume will be less than the heat capacity at constant pressure. Okay? For all systems this is true, and as I said, it's most noticeable in the case of gases. I can briefly explain the reason for this. If you imagine that you're putting heat in this diagram into these gases, so you're increasing the temperature, right? In this case, you increase the temperature and the pressure will increase. If you increase the temperature of a gas, you increase the pressure of the gas. But in this case, you heat the gas, its temperature increases, its pressure increases, but because it's now got a flexible lid, the increase in pressure will push the lid up. So as the gas is heated, it will expand in this case. But as it pushes the lid up, it is doing some work. Right? It takes energy to lift the lid. So that means some of the heat, which is going into the gas, is being used to lift the lid. Whereas in this case, all of the heat is raising the temperature. So in this case, all of the heat goes into increasing the temperature, but in this case, only some of the heat goes into increasing the temperature. So therefore, you need more heat to get the same change in temperature. Therefore, the heat capacity at constant pressure is bigger. And this is always true. No, it's not. It's almost always true. Almost always.